Let's discuss how to handle two independent categorical variables and to make comparisons between them. Suppose that we have a situation where both the input and response variables are categorical. Let's let I denote the number of categories for the input variable and j denote the number of categories for the response variable. A rectangular table having I rows, j columns and ij cells that display the possible outcomes is called a contingency table. Contingency tables can be created to compare two, three, or covariables. In order to understand what is happening within these tables, we need to discuss probabilities. If percentage denotes the probability that an observation falls in category I, j, then we consider it the joint probability for categories I and j. The set of percentages form the joint distribution of x and y. These probabilities need to sum to 1. Now let's discuss the marginal probabilities. The marginal probabilities are the sums of the probabilities across the rows and down the cumulus. We will denote them as psub plus for the rows and pi sub plus j for the columns. Examples of these for a 2x2 table are given in the slide. Each of the probabilities that we have talked about are parameters. You should realize that we will be working with sample data. So how does this change things? Note that we will replace all pi's with p's. We will use the sample cell counts, row and column totals, and the overall sample size to estimate probabilities. The sample joint probabilities are determined by dividing the cell counts by the overall sample size. This assumes that the sum of all of them subij equals the overall sample size. The sample marginal probabilities are determined by dividing the specific column or row totals by the overall sample size. This also assumes that the sum of the marginal totals equal the sample size. Let's let x be the input variable and y be the response variable. Most of the time we would like to set up separate probability distributions for y for each level of x. We will do this by constructing conditional distributions. In order to do this, we need the conditional probabilities. They can be calculated based on the formula in the slide. Let's look at an example. Here we have a survey of 1127 people who answered questions based on their belief in the afterlife. The gender of each participant was also recorded along with their answers. The results are given in the table on the slide. For this example, we will consider a person's gender as the input variable and their belief in the afterlife as the response variable. We are interested in the conditional distribution of belief given gender. Let's first create this distribution for females. Based on the data, we will find the conditional probability for a yes given that the person was female by dividing the total number of females that answered yes by the total number of females polled. We will do the same thing to get the probability for a no given that the person was female, except the numerator becomes the number of females that said no. Notice that the sum of the numerators is equal to the denominator. The conditional distribution is given in the slide. Now let's do the same thing for the males. The answers are on the next slide. Here are the results for the males. They are quite similar to what we observed for females. Two variables are said to be independent if their joint probability is equal to the product of the marginal probabilities. This does have some impact on the conditional distribution. If x and y are indeed independent, then the conditional probability is equal to marginal probability for the level of the variable not being conditioned on. This tells us that the level of the variable being conditioned on has no influence on the situation. In other words, it doesn't matter what you're conditioning on. There are overall 3 different types of studies. These are prospective, retrospective, and cross-sectional. A prospective study is one where a sample is taken and then the occurrence of an event in the future is recorded. A retrospective study is one in which a sample is taken and it is recorded if an event occurred in the past. Finally, a cross-sectional study is one where a sample is taken and the occurrence of an event happening in the present is recorded. Let's look at an example. This is an example based on lung cancer and smoking. The study was run in the 1930s in London, England. Patients from 20 hospitals admitted for lung cancer within the preceding year were polled about their smoking behavior. Then another set of patients that number the same that did not have lung cancer were polled about their smoking behavior. The analyst made sure that the patients had similar covariates such as gender. This is considered a retrospective study since the analyst is checking for an event that had occurred in the past, which is whether the patient smoked or not. Here are the results of the study. Notice that the number of patients in the groups that have and do not have cancer are equal. These are labeled cases and controls. This is because we consider this type of study a case control study. A case control study is a retrospective study in which a group of subjects where the event has occurred is compared to a group of subjects where the event has not occurred. The lung cancer example is considered a matched case control study since there is at least one control for each case. This study has what we call one-to-one matching. In most studies, we would like to assess the conditional distribution for the response given a level of the input. For the lung cancer example, we would like to study the conditional distribution of cancer given that a person smoked. Unfortunately, we cannot get that from a case control or specifically a retrospective study. These types of studies only provide us with the opposite conditional distributions. For this study and any other case control study, it makes sense to consider each column as a binomial sample. The problem in this case is that these samples would not be considered independent. We will discuss how to deal with this later in the course. Let's take a look at the conditional distributions for the lung cancer example. Here are the conditional probabilities for the lung cancer study. Notice that the probability that you smoked given that you have lung cancer and the probability that you smoked given that you don't have lung cancer are both quite high. This is probably a reflection of the time period. Now we probably still would like to get some idea about the opposite distributions. How are we going to do this? We assess the opposite distributions using Bayes' theorem. The problem here is that we need the overall probability that the event has occurred. This is usually difficult to determine with any precision since the rate of occurrence is usually larger for the sample than for the entire population. Now let's talk about prospective studies. There are two main types of prospective studies. These are experimental designs and cohort studies. An experimental design is a study by which are randomly allocated to groups, a treatment is applied and the occurrence of an event is then recorded. An example of this usually seen when dealing with categorical data is a clinical trial. A cohort study is one by which subjects choose which group they want to be in and the occurrence of an event is recorded. Let's look at how we could alter the lung cancer example so that it becomes a prospective study. The first situation would be considered an experimental design. This is because a subject is randomly assigned to be a smoker or not, then the occurrence of lung cancer is then recorded. This of course would never be done because of moral issues. The second study would be considered a cohort study since the subject decides which group that they would like to be in. Then the occurrence of lung cancer is recorded. This type of study again would not be run. Let's take a look at the probability distributions used for these studies. Prospective studies condition on the row totals, so we can consider each an independent multinomial sample. Retrospective studies condition on the column totals, so we consider each an independent multinomial sample. This holds for all retrospective studies beyond the case control studies as we saw earlier. Finally, cross-sectional studies treat the IJ cell counts as a multinomial sample since only the total sample size is fixed. Now let's discuss the difference between an observational study and an experiment. An observational study is one in which the researcher observes which group each subject falls in and the records results. Some examples of studies that match this criteria are case control, cohort, prospective and cross-sectional studies. Recall the definition of an experiment from earlier. The only type of study that could be run as an experiment would be a prospective study. Now let's move away from the types of studies and talk about the analysis of a 2x2 table. We will first discuss comparing two proportions. Usually we are interested in comparing groups based on a binary response from a 2x2 table. We will usually accomplish this utilizing the row totals. This comparison can be done assessing the difference in proportions or the ratio of the proportions. Usually the difference has more meaning when the proportions are near 0 or 1. Let's look at an example. The difference between 0.01 and 0.001 is the same as the difference between 0.410 and 0.401, which is 0.009. In this case, the ratio is much more informative. You can see that a ratio of 10 is much different than a ratio of 1.02, even though the difference is the same. Let's discuss the ratio in more detail. The ratio of two proportions is considered the relative risk. It is the ratio of the probability of a success for rows 1 and 2. The response and input variables are considered independent if the ratio is 1. Let's look at an example. Above are the results of an experiment used to test whether or not the regular intake of aspirin reduces mortality from heart attacks. Notice that one of the groups had taken the aspirin and the other a placebo. A placebo is a control to keep the experiment from being biased. In this case, the control group probably was given a sugar pill. It is usually best that neither group know if they are getting the actual aspirin or the placebo. This will remove the human mind effect from the experiment. Let's determine the relative risk from the study. Since this is an experiment, we will assume that each row is an independent binomial sample. Also, let's assume that a success would be that a heart attack occurred. The estimated relative risk in this case would be 1.82. Let's draw conclusions. The probability of a heart attack occurring for the control group was 82% higher than for the aspirin group. We could also state that the probability of a heart attack occurring in the placebo group is 1.82 times the probability of a heart attack occurring for the aspirin group. Notice that if we used the difference between the proportions, we would probably conclude that the difference was trivial. If this was a retrospective study, then the relative risk measure is meaningless since we will be conditioning on the column or response variable. So we need to come up with some measure that is independent of table orientation. We will use the odds ratio for this. Before we can talk about the odds ratio, let's talk about the odds. If the probability of a success is denoted by pi, the odds of a success is defined as the ratio of the probability of a success and the probability of a failure or pi/1 pi. Let's look at some details. The odds are always non-negative, and if they are equal to 1, then we are equally likely to get a failure or a success. A good example of this is a flip of a fair coin. We can get back to the probability of a success from the odds by using the equation in the slide. As an example, you should be able to convince yourself that if the odds are equal to 4, then the probability of a success is 0.8. Now that we have discussed the odds, let's move on to the odds ratio. The odds ratio is indeed the ratio of two sets of odds. For most 2x2 tables, it is the ratio of the odds of a success for one level of the input variable versus the odds of success for the other. As with the relative risk, the odds ratio can only take on non-negative values, and when the two variables are independent, the odds ratio will be 1. The odds ratio gives us an idea about the strength of association between two variables. Based on this, a value for the odds ratio and its inverse give us the same strength of association. Here is an example. If the odds ratio is 4, then the odds for a success for row 1 is 4 times the odds of a success for row 2. The inverse of this means that the odds of a success for row 2 is 0.25 times the odds of success for row 1. I would try to keep things consistent by trying to state the situation in terms of the odds ratio that yields a value greater than 1. Now let's define the odds ratio in terms of the sample data. We can define the odds ratio in terms of sample data by using what we call the cross-product ratio. Using the idea of a cross-product, you can see from the slide that the ratio of a success to a failure for row 1 divided the ratio of a success to a failure for row 2 can be simplified into the cross-product of the terms within the 2x2 table. We can get the sample odds ratio by substituting the counts within the specific cells in for their corresponding probabilities. Let's find the odds ratio for the aspirin example. We can conclude that the odds of a heart attack occurring were 1.83 times as likely for the patients taking the placebo than for those taking the aspirin. We could also subtract 1 from the odds ratio and state this as a percentage. In doing that, we would conclude that the odds of having a heart attack are 83% higher risk for patients who did not take the placebo. Notice here that the odds ratio does not change based on table orientation. This means that the odds ratio is the same regardless of which variable totals are fixed. This is not the case for relative risk. The advantage here is that we can use the odds ratio for case control studies. Let's look at the relationship between the odds ratio and the relative risk. The odds ratio is the relative risk times the ratio of the probabilities of a failure occurring. The relative risk and the odds ratio are approximately equal when the probabilities of a success for both levels are close to zero. This can be seen from the aspirin example. Let's do another example. Find the odds ratio for the lung cancer study and use it to approximate the relative risk. Here are the results. Notice that we will find the odds ratio using the cross-product method. We then substitute it into the formula and determine the relative risk. Since both the odds ratio and the relative risk are based on sample data, they are both considered estimates. We will need the ability to make inference on both of these quantities. Unfortunately, the distribution for both of these is skewed unless the sample size is large. This will make things a bit more complicated, but not impossible. In this situation, we want to know if there is a relationship between the response and input. By using the ratio measures, you should see that if there isn't a relationship, then the ratio should be 1. So under the null, we will assume that each ratio is 1 and then collect sample data to see if there is enough evidence to refute that assumption. Let's look at an example. Here are the results of a study taken over 5 years. It is a randomized study testing whether or not regular intake of aspirin reduces mortality from heart attacks. Let's use this example to make inference on the odds ratio. We will use the log of the odds ratio instead of the ratio itself. We do this because the log of the odds ratio has a distribution that is approximately normal. The mean of this distribution is the log of the actual ratio and the standard error is given in the slide. Now let's find the standard error for the odds ratio from the aspirin example. To do this, we will plug in the counts from the table given earlier in the slide. This will give us the distribution, but what about inference? We can create a confidence interval for the log of the odds ratio based on the normal distribution. The formula for this is given in the slide. Notice that this gives us the confidence interval for the log of the odds ratio, but what about the actual odds ratio? Once we create the intervals, we no longer have to worry about the distribution since the endpoints are constants. We now can do whatever we wish with them. So we will take the antilog of the endpoints, get the interval for the actual odds ratio. Let's find the 95% confidence interval for the odds ratio. Here is the SAS code to do this. The results are on the next slide. Here are the results. Notice that we get intervals for both the relative risk and the odds ratio. The estimate for the odds ratio is 1.83 with the interval being 1.44, 2.33. How do we draw conclusions about the relationship? Since the confidence interval for the odds ratio does not include 1, we can reject the null and conclude that there is a relationship between taking aspirin and mortality from heart attacks. There are also hypothesis tests for association that can be used. For this test, we assume that the cell probabilities are fixed. So under the null we know that the expected value for the cell counts are equal to the overall sample size times that particular cell probability. We refer to these as the expected cell counts. Now how do we make the decision on the association? In this case, we are testing for independence between a response and an input. Recall that if two variables are independent, then the joint probability is equal to the product of the two marginal probabilities. For this test, we assume that the variables are independent under the null. This being the case, we will assume that the definition for the expected counts given on the slide is true. Usually the expected counts are unknown, so we will estimate them using the observed cell counts as given in the slide. To decide on whether to reject or not, we will assess how close the expected counts are to the observed counts. The larger the difference between these two, the more evidence there is against the null. We will use the Pearson chi-square test to assess this situation. The form of the Pearson chi-square test statistic is given in the slide. Notice that numerator is the square of the differences between the expected and observed cell counts. You should realize that the bigger the differences are, the better the chance of rejection. We will need to get the distribution for this statistic in order to make inference. This statistic is considered chi-square as long as the sample size is large. In order to check this, we need to make sure that the expected cell counts are greater than or equal to 5. Let's talk further about the chi-square distribution. The chi-square distribution is non-negative, with the mean being the degrees of freedom. Based on the chart in the slide, you should be able to see that as the number of degrees of freedom increase, the distribution becomes more symmetric. The Pearson test statistic is considered a score statistic. Recall that it was shown that the score test statistic was the most reliable for tests for one proportion. We can also check for association utilizing a likelihood ratio statistic. Recall that the likelihood is the probability associated with the data for a given value of the parameter in question. We saw earlier that we could create test statistics and confidence intervals based on the likelihood. The likelihood ratio test is based on the ratio given in the slide. Recall that in most cases, the distribution used for contingency tables is the multinomial distribution. The likelihood ratio test statistic given the multinomial distribution is given in the slide. Let's look at some details based on this test. The LRT is also modeled well by a chi-square distribution with the same DF as the Pearson test. When the expected counts are large, the results from the LRT in Pearson will be similar. Now that we have defined some of the test statistics for association, we talk about what we are actually testing. Let's check for independence using the aspirin data with alpha equal to 0.05. Let's first find the expected counts. Here are the expected counts. Notice that the expected counts are quite similar for a given level of the response. This should not surprise you based on the observed counts. Now let's use these to find the test statistics. Given on the slide are both the Pearson and LR test statistics. Notice they are very close to each other in value. Also, the p-value is quite small. Let's draw conclusions. Since the p-value is less than 0.05, we will reject the null. This means that there is enough evidence to conclude that the variables are not independent. Recall that this agrees with what we saw using the confidence interval for the odds ratio. We can also create these tests in SAS. To do this, we will add the CHISC term to the table statement. Let's look at the results. The first two results in the table represent the Pearson and LR tests. The results occur as what we found.